Okay, the objective of this video is to show you a minimum working example of how to integrate the hard processor system and FPGA fabric um, in the DE1-SoC DE1-SoC FPGA board. Okay, and the example that we are going to cover basically instantiate a computer system which lives in the HPS side, okay? And also it has a little fabric, PGA fabric, that does a little computation. So the HPS is going to send through what we call Avalon a bus, okay, memory mapped bus, and we are going to use the lightweight bus, okay, which basically is sufficient for our purposes. We are going to send the number, 8-bit number, and then the FPGA will compute the number +1 and send it back through the out. So both of these interfaces are basically going to be what we call parallel input and output, on the Avalon bus, as we will see in a moment. Okay, so this is the objective. Assumptions, okay, before you can actually do this or follow me with Quartus, you have to first install Quartus version or Quartus Prime Lite, the Lite version or the Lite edition, version 18.1, and then update it using this update, which is the only one available during the recording of this video, okay? 18.1.1.646, okay? If you don't update it, you may get some errors here and there. Okay, so make sure that you update this version, which is basically, I think, in my opinion, the most stable version that we can use for DE1-SoC. And many other, of course, FPGA boards. Bottom line is avoid the latest editions or latest versions of Quartus Prime by all means, okay, because they are not stable and usually contain lots of bugs, both in the software and the IPs or hardware, okay? So you may find some yourself fighting some sort of a mysterious bug that you don't know where it's coming from, and this bug is due to using the a new version of Quartus that is not tested enough and that is not updated. Anyway, the other assumption is that you have Linux on DE1-SoC up and running, and you have successfully connected to this Linux box through USB connection, okay? Serial connection, basically. If you have done this, then you are ready. And I will actually give you, in the video description, I will give you how to do these two things, okay? This one, you have to do it on your own. I believe this is easy, okay? You can just look up Quartus Prime, right? And basically install the required version. It's important that you install the correct edition as well as correct version number. Okay, having said that, we can switch to Quartus now. And then I'm going to actually, not Quartus, okay, we will switch to Quartus in a minute. But before we do that, I'm going to run what we call the system builder for DE1-SoC, okay? I will also give you a link to download this, okay, which gives you basically a very, I mean, a ready project that can actually, lots of the things that you can automate things for you, okay? It can automate things for you. So first of all, you need a clock. And remember that we're going to create a minimum working example. So I only need the clock and the buttons for reset functionality. Okay. I don't need this, or any of these. Okay, so I'll just disable them. And I also need HPS, which is inside the chip as you see here. So only the buttons, the clock, and HPS. That's it. So I'm going to give my project a name, for example, I don't know, maybe HPS FPGA increment. Okay, increment. It just gets a number. The FPGA gets a number, then sends back an incremented version of it, and then just say generate. That's all. So you generate once you select your target directory. I'm going to save it here. So let me use the same name as I have just said. HPS FPGA increment. Yeah, and then where did it go? This is the one. So go inside and then save. You get a message that the project has been created, and that you have to add HPS system. We'll do that in a minute. So just close the system builder. Don't need it anymore. Okay, and then go to actually before you do that, one more thing to do. I need to copy this folder here, which I will also upload and make it available to you. It's an IP that contains a preset, as you see, that will simplify dealing with the HPS system, or HPS adding the high performance hard processor system. Okay, so you'll see why is this needed. So I will also add a link for the IP, which contains again the presets. Okay, presets that presets all the settings required for the HPS to work on DE1-SoC. Now I can go ahead and open my project. Okay, so I go to open project here, file, then open project, and then go to the directory projects. Okay, and then the increment, and then open the QPF, which is Quartus project file. Okay, once you open it, you'll find out that the project, if you select files here, the project contains only the synopsis design constraints file, which is useless in this case because you don't have any Verilog file. So you have to go back, and add your top module, okay? The one that has been created by the system builder, this one here, is just the top module. Okay, I'll just add it. Okay, and also I will add the IP. Okay, the IP inside preset. Okay, and then select all files, and then select the preset, add it. Okay, and then click apply. Okay. All right, so right now we have the preset added, and we have the top module, okay, which basically instantiates the top module for your circuit, okay, and the synopsis design constraints, okay, file. The first step is to basically right-click on this file, okay, and set as top-level entity. If you don't do this, you'll suffer a lot, okay? You'll suffer a lot if you don't do this. So please do not forget to set this as your top level entity. Okay, set it as top level entity. And then we can go and open up the platform designer to construct our computer system, okay, which contains the HPS system, okay. We need the clock anyway. What we need more is HPS, okay. Just type HPS here and select let me just maximize this window. Select this processor. So under hard processor systems, you have this processor. Double click on it. You have to be patient dealing with the platform designer as it is generating big files. So click finish. Yeah, just finish, because we are not going to set the values or the attributes manually. We are going to apply a preset to help us set the correct values for our board. So now we have this hard processor system added. Go to view and then select presets. And then you will see your preset under project. Okay, this is the preset that we have added. Click on it and then click apply. It will, the HPS system will shrink and you are left with a minimal system, okay, which only contains the lightweight bus, lightweight Avalon bus, which is sufficient for our purposes, okay. So in addition to the clock and HPS, we need to connect the input and output for the data in, for data in and data out systems, okay, input and output components to the bus, okay, and these are basically parallel input and output, okay, PIO. So double click that. Okay, now this is going to be an output from the HPS to the FPGA. So this is going to be our data in. Okay, remember that FPGA takes data in and then sends out data out to the FPGA, which is going to be data in plus 1. Okay, so yeah, I'm happy with 8-bit. Okay, it's an output. I'm happy with 8-bit. So just click finish. Okay, you can just change this if you want, rename it. Instead of PIO, you say, well, PIO data in, okay? And also, you need to add another one, we're not done yet, which is input to the HPS, okay? And it is 8-bit. It's going to contain data in plus 1, yeah, assuming there is no beyond, I mean, we're not basically interested in the extreme case where you add 255 plus 1, okay? You get a 0 in that case. So just, it's an input, an 8-bit. We're just worrying about the common cases for our minimum working example. Now, you see here that we have many errors, okay? And they will go away once we connect things together. First connections that you need to get, pay attention to the number of errors here, 5 errors. Go to systems or system menu, and then say connect or create global reset network. So now the errors are 3 only, okay? From 5 to 3. All right. Now the rest of the connections need to be done manually. All right. So this is the reset network. And then I need to connect the clocks, okay? So this one here, for example, this is the clock input of the lightweight bus. So we need that. I'm going to click on this circle to connect the clock output to the clock input of this HPS lightweight bus clock input. And also, each component in the connected to the bus is synchronous. So also the PIOs are actually clocked, so I need to connect the clock input for them. And let's just rename this to PIO, data out. I'm not done yet, by the way. We have to do something else in order to be able to access these parallel input-output in our Verilog code, okay? Also, I need to connect the slave here. These are slave components, and their master is the lightweight bus master, okay? So I need to connect this slave input to the lightweight bus master. And also this one, notice the errors are gone, but once I connect this slave to the master again, I get one more error here. Why? Because now once I connect the slave to the master, I get an address here, which is the physical address of the slave, okay, in the memory map, okay? So this is address 0, and also this is address 0. So this is a conflict of addresses, and this is what the error is saying. So to fix this error, you go to basically system, and then assign base addresses, and it will assign unique addresses to each component in your, to each slave in your computer system. Okay, and now the error is gone. You see here that this is going to be address 10 in hex, or 16 in decimal, and this is going to be address 0 in hexadecimal or decimal. Go ahead. Okay, not done yet. Okay, we need to be able to interface this data in and data out parallel input output with Verilog, and the way to do that is to export a conduit. It's called a conduit. You need to export it by double clicking here. Exactly. If you double click here, you're going to export a conduit. Let's call it data in. Okay, and then you'll get in your Verilog code a port in the instantiation module of this computer system called DE1-export. Okay, so you know that what we were talking about there. Okay, and also here, I'll click DE out. Okay, so once this is done, we are actually done completely. We have completed the entire computer system, and we can actually save it now by clicking Control S or going to File and then Save. It's not only that, so let's name it Computer System. Computer System, which contains basically the processor. It is a computer system in general, okay? Even though it's a small system, but it's still a computer system that is connected to Avalon bus, okay? A lightweight bus. The next step is to generate the Verilog code that basically models this computer system. And the way to do that, you go to here in the bottom right corner of the screen, there is Generate HDL button, click on it, and then you'll get this interface. And do not change anything, just click Generate. Okay, it is going to take a little bit of time, okay? But not too much, maybe 30 seconds or so. Don't worry about the warnings. Yeah, warnings are normal. You can just ignore them. Yeah. So once this is completed, okay, now it's complete, okay, with warnings. So just as I told you, these warnings are not really important, so just ignore them. Click close here, and then just for the sake of reference, we need the address map here. okay, for our reference in the when we go to Linux, okay? All right. So going back to Quartus now, we should get a message, I believe. It's used to say something here, but anyway, if you don't get a message, don't worry about it. You just need to basically add the Quartus IP that has been generated by the platform designer. So click on files here, right click on files, and then add and remove files, and then click on the three dots here. Then go to the computer systems folder or computer system folder, double click, and then synthesis folder, double click, and then select computer system.qib. And once you do that, click open here, and then it has been just apply and hit OK. Go back to Quartus now. You see it has been updated. I mean, the project has been or the QIP file has been added to the project, okay? And it contains many files. Among them is the computer system .v, which is a Verilog file that basically models the computer system that we just made, okay? I highly recommend that you go over this system and just examine its content, okay? All right, so having said that, the next step is to, one thing that I forgot to do is to go to the platform designer and then generate show instantiation template. How do you instantiate this computer system that you generated? Copy, using the copy button here. Okay, and then you go back to Quartus, okay, and scroll down until you find, you can put it here in the structural coding, and then paste, that's all, okay, paste the instantiation template, okay. You can see here that these are the port names, okay, you can see that these are the port names. All right, and I need to connect them to the parent module's signals, okay? And this is really time consuming, so I'm going to ask AI to do that for me. And I have prepared the prompt here for this purpose, okay? So I'm giving it the template, the parent code, okay? The parent module as well as the template, and I'm asking it to replace the placeholders with actual signals from the parent module. Just click enter. This is very simple to do using AI, okay? And this is the free version, by the way. Yeah. I don't want to copy the entire, I don't want it to change my file. I just need to copy the computer system instantiation. That's all. Okay. All right. So, oops. Oh, okay. It's a little bit difficult to work with. Yeah, I just need to add closing bracket. Okay, closing. So this is going to be. So notice that the DN_export. And you need to connect it to a signal here, and DOut_export, you need to connect it to a signal. So I'm just going to paste the populated values here from or ports the clock my clock is going to be clock underscore 50, which is basically a 50 megahertz clock, okay, taken from the board, okay? Remember when we used the system builder, we said generate the clocks for me, okay? Also, the reset is connected, which is basically, if you see an underscore in, it is an active low signal, and it is connected to push button number 0. Push buttons basically are 1 normally, and if you push it, it becomes a 0. So it's perfect for an active low reset, okay? And the rest are for the DDR3 connections, okay? And here we can just say DN and D out. Let's just replace this with DN and this with D out, okay? And we need to basically create wire 8-bit, okay? Remember it was 8-bit, right? DN, okay, and another one is wire, also 7, 0, D out, which is nothing but DN plus 1, okay? This is equivalent to an assigned statement, by the way, if you're not familiar with it. This is a shortcut for instead of just we're just combining both an assigned statement and a declaration of a signal, okay? So we're just receiving some number from HPS here, and then writing on the output DN plus 1, that's all, right? All the time. This is as simple as it can get. I mean, this is just, as I told you, this is a minimum working example. In your case, pardon me, in your case, you should include the Jacobi solver and then try to interface it with HPS, okay? All right, so this is done. The first step in the process now, in the compilation process, you need to do 2 compilations, basically. The first one will result in an error, or many errors, basically. And as you'll see, and then we'll run some tickle scripts that will fix these errors, okay? And then recompile again, okay? Because the compilation takes time, I will pause the video when we do the compilation. So let me just do the first pass of compiler here. And then pause the video. It is going to take about 2 minutes until the errors are reported about that, okay? So let me just pause the video and then come back when things are, when the compiler finishes, okay? Okay, now it's done, okay? The compilation is done, and as you see, we have, I don't know, 1,451 errors. And that is normal, okay? So go to tools, okay, once the compiler finishes, okay? Go to tools and then go to tickle scripts. These scripts are generated by the platform designer, okay? Click on the first script, which is basically P0. This is P0 is the model instance name. Okay, parameters. Okay, run it. Shouldn't take much time. It just finished successfully. And then pin assignment and run it. These are basically ticket scripts that configure SDRAM to work, okay? If you don't do that, you get these errors, filter errors. Okay, basically. So now we'll go through the second compilation attempt. Okay, hopefully this time we'll get zero errors. Yeah. So let me just pause the video because this is going to take more time than the previous one. Okay, good news. We have finished compilation in about 4.5 minutes, and we got zero errors, which is great. Okay. Good practice is to look at the critical warnings. Okay. But they are really not that critical to our case, which is basically related to pin assignments, but always have a look at the warnings as well as the critical warnings. Luckily, in our case, we have no warnings that need to be taken care of. Okay. Now, the next step is to go to, assuming that your board is connected and up and running. Okay. You go to programmer. Okay. And in the programmer, you get this chip, but actually you should get two chips in sequence. Okay. So to get that, you hit auto detect. Okay. And then select the second one, which is our chip, basically. Second one is our chip. Click OK, and then you get the two chips, basically the fabric, the FPGA fabric, which is this one, okay, and the HPS. We're not going to change the HPS, but we are going to change the Avalon interface, okay, which is programmable. So this is the we are going to update our or to upload our program here. Okay, and we have to click change file. Okay, the programming file, and the programming file is available in or under output files. This is it. .sof. You see. Click open, and then once you select the file, you can actually change this checkbox to checked. So now we have requested to program this part of the board. Now, once this is done, we can click on start. We get successful, fortunately. Now it's time to connect to the board. Okay, through USB. I just double click that, connecting to the board. So now the board is actually connected. I have created this file, which is basically main.c. And if you would like to look at the content of this file, I'm going to also include it in the video description as well. But in your case, you need to write another file, of course. It's just a bunch of includes at the beginning, and then definition of constant defining the lightweight bus, which is basically the physical address of the lightweight bus. This is taken from, the data sheets. Examine the data sheets, you'll find that this is the base address of the lightweight bus. And this is the physical address. It's not a virtual address. Now, the problem is that we are in Linux, which is an operating system. And as a user, as users, we are dealing with virtual addresses rather than physical addresses. So we cannot actually deal with the address right away. So what we do is we consult a little table in the memory called the page table, basically, which converts a physical address to a virtual address for us using the mmap. I believe, yeah, the function mmap, memory map. Okay, it gets a bunch of inputs. Okay, among them is the address itself, the physical address. Okay, and it returns back a virtual address. Okay, for you. So the way that this program works, okay, is that it is generic. Okay, I have actually, let me just, oh, I need to zoom or maximize the window and remove Zoom's interface. So, yeah, basically the way this program works. Okay, let me just remove FPGA. This is the binary, and also remove a.out. Okay, so I'm not going to talk about main2.c. It's just the same as main1 and main.c, but it contains some printf statements to show you more printf statements for verbose, increase verbosity. Okay? So I'm going to compile this. You don't need to actually compile, use a cross compiler for that, for this simple cases of ours, okay, like your project or this one here. You can use the compiler in write your program exactly in the inside of the HPS Linux. So you can say, well, via Vim, which is installed hopefully in your system, or you can use Nano if you want. So Vim will give you a chance to edit the code, and then once you're done, you can compile it using GCC, FPGA, read, write, okay, and then main.c. And the way the program works, so this is the binary file now I have compiled. If you just try to run it, that will give you the usage. Usage is basically FPGA read write, and then you give it a read command or a write command, one of them. And if it is a read command, you just give the physical offset, okay, and it will translate it to virtual inside, and then print the information for that, print the content of that address for you. If it is a write, then you have to provide the address as well as the value to write. Okay. Now, I'm sure that you know why I left this platform designers address map open. Okay, because I need to use this address. DN is at address 10 hexadecimal, and DOut is at address 0 hexadecimal. So let's try to read the addresses first, what's stored in there, and then try to write something. So first of all, FPGA read write, okay, and then read. Data in was address 10, right, in hexadecimal, which is 16 in decimal. So yeah, so basically in address 10, we read 0. And nothing is written there, so it assumes it happens to be 0 right now, okay? So we expect the address 10, address 0, which is basically DOut, to be 1 because it's 0 plus 1, right? Yeah, this is the case, it's 1. Now let's change the DN right, 0x10. Let's write, for example, 0x50, okay, 50 in hexadecimal. Okay, now this is written 50 in address 10. Let's just make sure we read it. Okay, it's 50, right? Now we want to read the out. We expect it to be 51, and it is the case. Okay. All right. So this is just a simple example that shows you how to interface FPGA and how to interface HPS with FPGA. Now, once you're done, if you want to keep or to protect your micro SD card and from corruption, from data corruption, always do not turn off your FPGA immediately, no, but execute this command sudo halt. Okay, once the system is halted, okay, you can actually turn off your board. Okay, all right, that's it. Let me just stop recording. Thank you for watching, and I hope that you guys can implement this bonus part for your project.